derivation we're about to do, the first time I did it for a class, it took about 2 hours. I found an easier one. Well, actually, I'm going to do a prequel derivation first. It will not take 2 hours. Well, let's see if I can do this without making mistakes. All right, so again, I got my S frame here, my S prime frame. S prime frame is moving to the right at some speed. Well, I think I did U last time, so we'll stick with U. Now, we just did the derivation of an arc particle that's traveling in the same direction that S prime is moving in, but now let's deal with a particle that is not moving in that direction. One that is moving in a direction that has perpendicular component. And then what I just did, that was W. W, the speed of the particle with respect to S prime. What were the letters I used?
Yeah, it was W for that one.
W was with respect to S.
For S prime.
W is S prime, okay. So W was the velocity. So it's traveling at some speed. W with respect, that's the velocity of the particle with respect to S prime. And then the velocity of, I guess V was the velocity of the particle with respect to S. So if at W here, I have two components. I got a component in the direction of movement and a component perpendicular to the movement. So W, if I broke it up into its components, I'd have the W, well, basically I'd have WX and WY, assuming X, Y, and Z coming out at us. So the distance, so W would just be dy prime dt prime. And if I'm looking at comparing the two reference frames, I know that x prime is equal to gamma x minus vt, or actually ut. Y prime is equal to y. X prime, z is next. Z prime is equal to z, and t prime is equal to gamma t minus ux over c squared. So dy prime dt prime, well, dy prime is the same as dy because the y value doesn't change, so that's dy over dt prime. In other words, the derivative of this. So that would be, so dt prime is equal to gamma dt minus u over c squared dx. Use the constant because we're dealing with special relativity. So the y component of w is going to be dy over gamma dt minus u over c squared dx. We gotta multiply both top and bottom by 1 over dt. And so I get dy dt over gamma 1 minus u over c squared dx dt. Dx dt would be the y component of the vertical component of how fast it's going, which would be v sub y. So dy dt is V sub y over gamma 1 minus u v y over c squared. Check here, make sure I didn't get something in the wrong spot. So that's prime, yada, yada, yada. Vy prime would be Vy over Vx. Slight difference in my notes here. Oh, that's dx dt. Vx. So how fast the particle is moving in the x direction from S's point of view. There we go. So now, I have two scenarios here, of course, because I have two different points of view. In the S frame, I have a particle that is moving up at some speed u sub 0. I'm going to apply a force to it. And as I apply the force horizontally, it's going to accelerate in the horizontal direction, and so I would expect the particle to be moving like that. And then I stop applying a force to it, and so at that point right there, the particle is moving in that direction, where this component would be, I keep something similar to my notes there, is V, and this is u. Now there is a difference here between u and u sub naught. We are assuming that there's going to be some relationship, something that's going to change because of speed. Because think about it. If I cannot pass the speed of light, then if I apply a force to an object, so I apply a force to an object, in Galilean relativity, I apply a force to an object, it's going to accelerate. If I apply that force long enough, it will eventually pass the speed of light. But it's not going to happen in special relativity. If I have F equals ma, A is equal to F over m. As I get closer and closer to the speed of light, my acceleration has to change. If I do speed versus time here, then yeah, it might start out linear. But if that's the speed of light right there, it's going to have to eventually get closer and closer, but never actually hit it. Well, one explanation for that, assuming that my force applied is constant, is that my mass is changing. What we're doing right now is deriving what is the relationship between the mass of an object and how fast it's going. Now, in this initially here, u sub 0, we're dealing with a speed that is slow enough that the mass is close enough to the rest mass. So I have, at this point, the rest mass, m sub 0. Over here, it has some mass m. If we establish an I hat and j hat, I know that F is equal to dp dt. And my force, and I also know that my force is in the I-hat direction. Because I define the problem so that the force is pointing in that direction. My momentum, mass times velocity. So this would be basically if P, got a lot of clutter here, let's get rid of this stuff. So if P is P sub x I hat plus B sub y j hat, then this would be dpx dt I hat plus dpy dt j hat, which has got to be equal to f I hat. And so the change in the momentum in the y direction with respect to time has got to be 0. There are forces in the y direction and the j hat direction, so it's not earth shattering. I hope. Now, let's take a look from a different point of view. I can get rid of that. I now want to look at the S prime frame of point of view. And S prime is going to be moving to the right at a speed v, the same v as that. So from the S prime point of view, this particle is traveling in the negative direction, but at the end, it's just traveling straight up. So from the S prime point of view, I have this particle that's zipping off to the left. Until its vertical component, horizontal component matches that, the speed of S, and then it's going to be moving straight up at some speed u sub naught. It starts out with some component to the left of v and an upward speed of u. It starts out with some mass m and ends up with some mass n sub naught. So again, we're making the assumption that the mass is affected. Momentum is conserved. So mu is equal to m naught u naught. Yeah. The S prime frame. Oh. Prime. So from that, we have m naught u naught equals mu. And from this one, we have mu prime is equal to m naught u naught prime. That should work. Yeah. Quick look to make sure. So mu naught prime somehow we got a subscript wrong. Mu. Yeah, probably get this better ironed out. All right, just take a moment here. I forgot the reference frames. Jeez. All right. this speed right here should correspond to that speed right there. So this u here is actually not u, it's u naught prime. It's how fast it seems to be going from the prime frame. This right here should correspond to that. So this should be u prime. And so my equation here should be m naught u prime equals m u naught prime. If I want to get it in terms of the relative velocities here, so, or actually, let's see, I want to get it in terms of m naught to m. So if I divide like that, I get m over m naught times u over u prime is equal to m naught over m times u naught over u naught prime. Getting the m's on one side, I get m over m sub 0, so my mass over my rest mass, that ratio squared is equal to u sub naught u prime over u sub 0 prime. These are all speeds that are perpendicular to the actual motion of my prime frame. We're going to need that. So it starts out where this object is moving up. My axes are a little bit off there, but we start out with this thing moving up like that before the force is applied, and so u sub naught is going straight up. All right, so before Vy is equal to u sub naught. Vy prime is equal to u naught prime. Vx equals 0. There is no speed in the x direction. And so looking at my relationship here, u naught prime is going to be equal to u sub naught over gamma 1 minus 0, because v sub x is 0. So u sub naught over u sub naught prime is equal to gamma. There we go. Feeling much better now. Let's over here. After the acceleration, we have Vy is equal to u. Again, it's the velocity in the vertical direction. Vy prime is equal to u prime, and Vx is equal to v. So how fast it's going in the non-prime frame. So u prime, again, plug it into this equation right here, is going to equal u over gamma 1 minus uv over c squared. So combining our two things over there. My relationship between the mass over m sub naught squared equals u sub naught over u sub naught prime. U sub naught over u sub naught prime is gamma times, there's u sub naught over u sub naught prime, and then I times u prime over u, which is 1 over gamma 1 minus uv over c squared. recognize that u is how fast v, the s prime frame is going with respect to s, which at this point right here is speed v. So u and v are the same thing, and so I end up with gamma canceling out. I'm left with 1 over 1 minus v squared over c squared. So u equals v, which is just gamma squared. So mass over m sub naught would be equal to plus or minus gamma. The negative does not make any sense. I'll add to that in just a moment. And so we end up with the mass of an object is equal to gamma times m sub naught. So we have the mass that is measured in a moving reference frame is equal to gamma times whatever the rest mass is. If I were traveling at 0.866 times the speed of light relative to you, and you tried to measure my mass through probably a collision, my mass would come out to twice what it normally is. What my rest mass is, I should say. My rest mass is about 100 kilograms. You would see my mass as being about 200 kilograms. Two addendums. One, not every physicist will agree that it's the mass that is equal to gamma m sub naught. Some will make the claim that it's actually mv is equal to gamma m naught v. I guess probably there should be a prime in there somewhere. That it's not the mass that changes, it's the momentum. From one source that I read, that seems to be a generational thing. So if you see someone who goes, no, the mass can't, it's not the mass that changes, it's the momentum, they're probably younger. The other bit is we end up with this plus or a minus there. And there's actually, I'm going to hold off on that. It is going to be plus. Later on, there's going to be a plus or minus that I need to address. That's what we get to